Okay, we have our next Cram video is going to be on energy and work-kinetic energy theorem and the conservation of energy. We'll start with a cart traveling along a track being pulled with a pulley system here and a mass. Okay, well, we know that there will be a force applied here acting on this force sensor, so we'll call that force applied. And of course, that's going to act through a distance here. So our equation work equals force times distance cosine of theta does apply. And of course, we'll see that this object will change in its kinetic energy as it's being pulled. Okay, now we're parallel, so the angle theta is going to be 0, so the cosine of theta of 0 is equal to 1. Now what that's going to do is the work done is going to go into the change in kinetic energy, okay, of this object here. So we're going to say force times distance is equal to 1/2 mass times v2 squared minus 1/2 mass times v1 squared. And of course, if we start at rest, then v1 becomes 0. Now, we have the same kind of thing going on here with this mass. There is a force applied. This time it's force of gravity. Okay, so we'll just label that as mg for force of gravity. Now that's going to be operating through the same distance. Okay, and we can use the same theorem to deal with that. So in this case, of course, you're getting a work caused by the change in gravitational potential energy here. So delta GPE. Okay, so in that case, we can go delta GPE is then going to equal the change in kinetic energy for that system over there. Except when we do this, the change in gravitational potential energy of this one going downwards has to equal the kinetic energy of this object plus the kinetic energy of our other object moving. So it's going to look something like this. The change in gravitational potential energy is going to equal the change in kinetic energy of, we'll just call that the cart, plus the change in kinetic energy of the, let's just call that the mass. So if we look at it from the perspective of this thing going downwards, and not just the isolated system here, our gravitational potential energy change is going to equal, then we'll have a 1/2 mv2 squared minus 1/2 mv1 squared, all in parentheses here, plus 1/2 the mass of this times its v2 squared minus 1/2 the mass of this times v1 squared. So two ways of looking at the work kinetic energy theorem. Okay, now what about doing something simple like raising books going upwards here? Okay, in that case, our work is definitely going against gravity there. So the work in this case is then going to go into equaling the change in gravitational potential energy plus the change in kinetic energy, assuming that we're moving the books up at some point. So how can we really approach this question here? Well, the work is going into two types of things that are conservative. Okay, and we can maybe call these conservative energy types maybe. So the work is going into gravitational potential energy and also going into kinetic energy. So there's two things here. So our net work is going into some kind of conservative energy. Now, of course, there's no friction here. Okay, so we can call that maybe the net work. In this case, it's all conservative. What if there was friction? Then we would subtract, I'll just label it down here, the work of friction, okay, which is non-conservative. Okay, so I'll label that as non-conservative. So whatever work net is done is going to go into whatever's left over would be maybe gravitational potential energy and kinetic energy when we're done. And then we can label this as maybe work net equals the change in gravitational plus kinetic and then let's say minus the work of friction here. Okay, and all of the equations can be considered in this fashion. So if all of the work goes in the conservative, okay, then we usually don't say the net work. If there is some friction taken away, then we do say the net work. But indeed, the net work, whatever's left over, will go into some kind of conservative energy, some kind of potential energy and kinetic energy. Now, if you're going just along a horizontal surface, then that is just kinetic energy. And that's how we handle the work kinetic energy theorem.